Normally I don't read the bios in their entirety, but Al provided a nice brief one, so I'll go ahead and read. I went ahead and found Al actually on LinkedIn, convenient tool, and he had the background and something to speak to us about tonight. I was interested in, I started off looking for a theme on medical computing.
We've done that too.
So Al Wegener is CTO and chairman and founder of Samplify Systems. It's a venture-funded IP licensing startup whose compression and acceleration products reduce bandwidth and storage bottlenecks in electronic systems. Samplify's products offer lossless, fixed rate, and fixed quality compression modes that users control in real time. Mr. Wegener has developed products for wireless, pro, and consumer audio and defense applications. So Al holds an MSCS from Stanford University, a BSEE from Bucknell University, and is named on 30 U.S. patents. So thank you, Al, and welcome Al to speaking tonight.
All right. Thank you, John. Well, good evening, everybody. My name is Al Wegener with Samplify Systems. A little bit about myself. I'm a signal processing guy. I'm a DSP guy. I've worked in defense electronics, pro and consumer audio, and wireless systems. And I more or less fell in love with the technical problem of compression in the 1990s when I was working at a pro audio company. In the span of 2 years, I saw an entire industry, professional audio post-production, which is film studios, recording studios, and radio stations, switch from saying, what do you mean audio compression? You're throwing 3 out of 4 bits away. It must sound like crap. 2 years later, they said, wow, with compression technology, we can now play 20 to 25 live audio channels off a SCSI disk drive instead of 4 or 5 that we had just 2 years ago. So the benefit of compression solving an I/O bottleneck outweighed any drawbacks that the audio community was nervous about at first until they put the headphones on and thought, oh, well, sounds the same to me. So tonight I'd like to tell you a little bit about how that same benefit of compression could be used in all kinds of computer systems. We'll be talking about wireless base stations, high-speed imaging, supercomputing, high-performance computing. So there's a lot of applications where this compression technology could be used. And if you have questions as I'm going, please feel free to raise your hand and I'll try to answer the questions as I'm going. And by the way, Samplify is another one of those companies that has a few recs open. If we have any RTL, FPGA designers or verification engineers out there, I have business cards here. Feel free to send me your resume. So what we'll be talking about tonight is multi-core and the memory wall. Many of you may have heard of this problem that as we keep adding cores to chips, I/O becomes a problem. So we'll go into some of those details. We'll give some examples from Intel and AMD CPUs as well as NVIDIA GPUs. And we'll talk a little bit about supercomputing. About 1.5 years ago, Samplify had a new investor, which is Schlumberger. Has anybody heard of Schlumberger? Oil and gas exploration? Good. Sometimes people haven't heard of it. 110,000 employees, $24 billion a year in sales. So believe it or not, they have some pretty serious I/O bottlenecks that start at the sensors and they end in the supercomputer. And we're helping them initially with some supercomputer bottlenecks. There are some non-scalable memory wall solutions, and these are the ones that everybody in computers is using today. PCIe Gen 2 goes to PCIe Gen 3. DDR3 goes to GDDR5 or LPDDR2. You throw bits or pins at bandwidth problems. And those techniques, I would claim, are not that scalable. We'll talk about a couple other scalable solutions besides compression. Those are interesting because some of you may have heard of Hadoop. And basically the idea is to move the computing to where the storage is rather than taking the data from a consolidated storage array and bringing it back to where computation is done. And then I'll spend maybe half the slides talking about compression. I will give you a real-world example about a pressure transducer signal from an unnamed company and talk about some of the bandwidth bottlenecks that customer had and how Samplify has solved those bottlenecks. Okay, how did we get here? Multi-core and the memory wall. So in 2004, Intel, among other semiconductor companies, realized that they couldn't keep scaling the clock speeds. 2 gigahertz went to 3 gigahertz. They talked about 4 gigahertz, and then they punted. So they decided it was better to put more cores on a chip and leave them at a low clock rate because the power became more manageable. And since 2004, in order to stay on Moore's law, the CPU and GPU vendors kept adding more and more cores. Well, this is great if the packages had only scaled, but scaling packages is a difficult thing. As of this year, we have Intel Ivy Bridge with 10 cores, up to 10 cores, each having the AVX acceleration units, 256 bits wide, doing 4 64-bit operands at a time. And the Kepler, recently announced NVIDIA Kepler processing chip, which is becoming very popular in the so-called GPU, general purpose GPU processing. So basically using graphics chips for supercomputing. From a different area, supercomputing, has anybody heard of the top 500 list? Top 500? So these are the most powerful supercomputers in the world. The leader, as of today, is a supercomputer in Japan built by Fujitsu. There are several, I think 5 of the top 10 are in the US, but surprisingly, many of them are outside the US. So in supercomputing, they have had an I/O problem for quite a while, and it's only getting worse. And I'll have some details about that as in a few slides. So basically what we'll talk about tonight is if the supercomputer is having I/O problems, just getting the operands to the compute units, is that a problem that we're going to be seeing when we start having 1,500 cores on a socket, a GPU socket, the Kepler chip from NVIDIA, as we start putting 10 and 20 cores onto Intel chips, is I/O going to be a problem, as it has been with supercomputing? So this kind of sets up the memory wall bottleneck. At the highest speed, 2 gigahertz, nominally could be 3 gigahertz, you have registers where the registers can be accessed as quickly as the CPU is running. Then we have L1 cache, L2 cache, flash or solid-state disk, and then Ethernet, and then down here is the turtle of storage. I didn't even bother putting tape drives on here, although I have to say that Storage Tech, which was purchased by Oracle, still has a pretty big business in doing backup tape drives, tape cartridges. And there's the memory wall, right around 1 gigahertz. So the idea is that if your cores are going at 2 and 3 gigahertz, and your I/O is going at 200 megahertz, you have a problem. Your cores can theoretically go very fast, but if they don't have anything to do, then they're just sitting there idle, waiting for data to arrive to populate the cache. I was told when I started putting slides together that up and to the right is the direction you should always aim for. So here is basically an up and to the right graph of, on the right we have pin counts going up to the famous 2011 ball Ivy Bridge and Sandy Bridge socket. And on the right here, the blue lines are gigabytes per second for either QPI or front-side bus. Intel made a change a few years ago where front-side bus just couldn't be scaled anymore, so they pulled the memory controller into the chip and decided that they were going to access DDR directly from the chip. Well, this all looks great, but look at this column right here. The number of cores has been increasing. So bandwidth has been going up, pin count going up. It all looks good until you look at this. Then you start saying, what is the bandwidth per core in gigabytes per second? And here's the number of cores. So basically, here's the number of cores. We had unicores up till about 2004. Then we started going to 2 and then 4. And now we get 6, and eventually we'll get to 10 or 20 cores on Intel processors. And as a result, the processing bandwidth per core has kind of topped out here somewhere between 4 and 5 gigabytes per second. Sounds like a lot, but the cores are starting to be idle more than they're computing, depending on the application. So here's another up and to the right. Looks pretty good. We go from PCIe Gen 1, and then in 2007, NVIDIA switched their interface to 16 lanes of PCIe Gen 2. Very often when I quote these throughput rates for GPUs, people think, well, how could they possibly have an I/O problem? 16 lanes of PCIe Gen 2 is 8 gigabytes per second. 8 gigabytes per second. Sounds like a lot. If you have 512 cores in the latest Fermi class machine, you have a lot of GDDR bandwidth, but the PCI speed, notice that this is kind of flattened out, but they've gone from 64 cores to 512 cores. So if you now divide the bandwidth into the number of cores or the number of shaders, you get a pretty sad-looking curve. And all of a sudden, we've gone from having 20 megabytes a second down to below 5 megabytes a second per core. As I was putting these slides together, I thought I would do a little checking to see, does anybody else notice this trend? And I found a bunch of articles. The most recent one was an article done by Russell Fish, who has his own startup somewhere on the East Coast. And he did a 3-part series, which I recommend to people, talked about the future of computers. And his first one talked about multicore and the memory wall, which is exactly what we're talking about tonight. His company has a slightly different solution, but it's also an interesting one. And he came to the same conclusion here, the lack of memory bandwidth and contention between processors. You keep putting more and more cores on there, but the cores are stepping on each other's toes, and they're all contending for a limited amount of DDR memory or a limited amount of PCI Express bandwidth. So 2 slides about supercomputing. What are we seeing in supercomputing? For those that aren't familiar with it, this is basically you slap somewhere between 500 and 10,000 x86 sockets together, and you connect them with either a 10 gigabit Ethernet switch or InfiniBand links, InfiniBand switches, and with that you can build a supercomputer. The data distribution problem in supercomputers is enormous. And as an example of that, we'll take the number 7 supercomputer in the world, the Pleiades supercomputer at NASA Ames Research, just a few miles from here, and they run an application called General Circulation Model. And it basically is simulating ocean flows. So regardless of what you think about global warming, this is a big problem, and they're basically using physics equations and finite element analysis to simulate how does temperature and density interact in our oceans and then affect climate. Now, here's the interesting number. They're getting a whopping 1.4% utilization out of their cores. So if you bought 1,000 MIPS, you're getting 14 MIPS of throughput. 1,000 MIPS, and you're getting 14 MIPS of throughput. Here's the reference if you want to look that up. And again, another worrying trend is here is they'll double the number of cores, and all of a sudden the performance goes down or the utilization goes down. So you keep buying a lot of processors, but you're just creating a big heat problem, and your boss won't be happy because you need a megawatt for the new equipment you just bought. The public information, Schlumberger gets 2 4-megawatt feeds from their local power district in Houston. 4 megawatt feeds. And if one of them goes down, they can keep computing because they have a second one. In exascale, which is this slide right here, DARPA did a study in 2008 about exascale. So exascale means 10 to the 18th. How do you get 10 to the 18th flops out of a system? And what they concluded there was that at exascale and above, the cost of power per year exceeds the cost of acquiring the equipment. The cost of power per year exceeds the cost of acquiring the equipment. So bring a big wallet if you're going to do exascale. So this graph is probably the best description of the memory wall. Here's this access speed, access time of DDR, and DDR kind of, it should have a little jump here where you went from DDR2 to DDR3, but it's kind of a blip on this scale. And then here's the CPU cycle time. This is Moore's Law, this line right here. This last blip here from 2004 on, these blue triangles indicate where we've gone from multi-core. This is basically 2 cores, 4 cores, and 8 cores. So we see a speed up off of the single core line, but look at this gap here. So multi-core is making this gap worse. And what the exascale guys concluded was that if you're going to get to exascale, you have to have a 16x increase in raw memory bandwidth. So this is DDR. And you need to have a 100x increase in the speed of what they called I/O. So this is your plain old disk drives. One way to do that is to buy 100 times as many disks and make really fast RAID controllers, but that's hard. Question?
Are you going to talk about cache? And don't they put a lot more cache on all these things to help that up?
How about there? All right, but hold that thought because in about 6 or 7 slides, I will specifically address cache and a new phrase that I hadn't heard till last night. So stay tuned. Okay, so here are non-scalable solutions. If the general problem we're trying to solve tonight is we've got all these cores and we want to keep them busy and we've got to keep them fed, how do we do that? One way to do that is you just add more I/O pins. Okay, the 2011 ball Intel Sandy Bridge, that's a lot of pins. If you want to double that, that's a very expensive package, and you got to put the little heat sink, you know, that little heat sink that's 4 times the size of the chip. That's a problem. So you could add DDR ports or SerDes lanes. We actually have seen several companies doing this. If one DDR port is not fast enough, then add a second one or a third one. NVIDIA Fermi has 6 64-bit GDDR5 interfaces. 6 ports, 64 bits wide. You need two pins per lane. You have, I think, 700-ish pins out of a 1,300 ball package just for memory I/O. So I don't think that's scalable. Faster I/O, let's use SerDes. Well, SerDes is hard, and SerDes is hot. If you take a look at some chips, Hans works at Altera, 10 and 28 gigabit transceivers take a lot of area, and they take a lot of power. So, what's that?
Certainly the ones from China.
Yes, the ones from Xilinx do. Then Alteras are much more power efficient, I'm sure. But it also means that you have some expensive IP blocks if you're a startup like Samplify and you wanted to actually build a chip with 10 or 40 gig SerDes in it. You're looking at, it used to be somewhere between $3 and $4 million to a company called Snowbush, which had 10 gig SerDes blocks. How about more cache? The gentleman asked about cache memory. Well, 20 megabytes on the cache. Is that enough? Hold that thought. It's not enough. Think about how much area we're now using up. It used to be that I used to work at Texas Instruments and wrote a lot of code for TI DSPs. And you look at the die photo, and you'll see that 2/3 of the area was the processor, and you have some peripherals and memory on the outside, and that was the chip. If you look at the die shots of today's processors, 30 to 50% of the area is cache. Our leading edge Intel and NVIDIA, they're turning into memory companies. How about stacked die? This is, we all have cell phones, right? And most people that know how cell phones are built, if you look at Qualcomm Snapdragon or Marvell Armada or NVIDIA Tegra, they have some 2 and 4 core ARM processors on the lower die, and on the upper die they put LPDDR2, and they sandwich those together and pour some plastic over it, and off you go. Well, can't we just keep stacking that stuff up? Through silicon vias are becoming a limiting factor, and you also have a yield problem. The more die, even if they're proven good die, that you stack together, you're going to have some manufacturing fallout from that. So I don't think that's very scalable either. And then there's optical. I won't say too much about optical, but there's always 3 to 5 articles a year where they say, oh, well, we'll just use photons for computing. Well, I don't think it's there yet. Okay, so let's talk about 2 solutions, hardware-software prefetch and dedicated cores being used for I/O instead of computation. And then we'll get to my favorite topic, which is compression. And I'll be using this term APACS. This is a trademarked phrase that Samplify is using to talk about application acceleration. Our CEO down here took liberties with the spelling of the second word, but we like it. Okay, so here's an article that Intel wrote about medical image processing in 2006. And what they were trying to say is we're trying to render, I think this was an ultrasound application, we're trying to render some images, but there's just a huge volume of data that you want to get up to the screen. So you want to try to do prefetching. You want to say, I know that in 2 microseconds I'm going to need this 2 megabytes of pixel data, and I'm going to throw that up on the screen. So I'll know ahead of time, I as the software programmer, that I want to prefetch that data, make sure it's in cache, so that 2 microseconds later when I'm done putzing around with my code, that I can throw those pixels up on the screen. So they did some comparisons that showed you could have both hardware and software prefetch. Hardware prefetch is where the chip tries to discover what is the pattern of access, what are the access patterns for the operands that are being brought into the chip, and then it automatically brings those in, just says, well, if this has been the pattern for the last 2,000 words, I'll use that same pattern and just keep going even though the user hasn't asked for it yet. That's hardware prefetch. Software prefetch is what I mentioned earlier, where the programmer has a good idea of when the data should be scheduled to come in. So you can get a speed up with this. The Intel paper showed that you could get a speed up of maybe up to 20% by doing hardware and software prefetch, the combination thereof. So one of the things about the memory wall is that if you optimize data prefetch, it can make your apps run almost 20% faster. That number in mind, 20%. Here's an idea. We have 4 cores. Why don't we have one core be the traffic cop? He's the one that's going to say, okay, you stop, you go, let's get the data into the chip. And we'll have 3 of the 4 cores doing computation. You can get better throughput that way. You basically have one processor out of 4 doing all the I/O, and that is a better way to schedule data coming into it. Now, it does require that these cores have a pretty high interprocessor communication bandwidth, such as Intel's QuickPath Interconnect or AMD's Hypertransport, but that is a practical solution. Another interesting technique I saw a few months ago was something called CUDA DMA. Has anybody heard of CUDA? Okay, good. About half of you. CUDA is the software environment that NVIDIA has developed in order to support doing general computations, supercomputing, if you will, on NVIDIA GPUs. And it's a cool, clever language. They've done a good job of taking an algorithm, a uniprocessor algorithm, sequential, written in C, and then getting that to run on hundreds and thousands of threads on the GPU. A little asterisk with CUDA, you have to use their memory controller. You have to use their memory management algorithm. So you write the algorithm, and it gets parallelized by their software, by the CUDA software, but you're totally dependent upon their I/O. This article, which was written by these 3 guys from NVIDIA, had the idea that, well, let's actually have a DMA warp or a DMA thread, and then let's have a compute warp or a compute thread. So basically, this is the same idea, but now all the threads are doing some I/O, and they're all doing some computation, and then they're doing another I/O step. So it turns out this is another way that you can speed things up. You can either say that 1 out of 4 cores is for I/O, or part of the threads are for I/O and part are for computation. All right, now we're about halfway through, and this is really the first slide where I'll be talking about compression. Compression is seen by many like analog design as a black art, but I've spent my last 5 or 6 years trying to let people know it's not that complicated. We've had the Lempel-Ziv lossless compression algorithm for ASCII text, for executables, for object code, and it's been around for 30-some years. The patents have expired, LZ77, LZ78. It seems like a long time ago. VMware is one of the companies that today, everybody's heard of virtual memory, virtual processors, virtual machines. VMware is a leader in this. They're a multi-billion-dollar company, and they are now doing compression. They're using lossless compression to say, okay, this is the operating system managing 4 KB pages. These pages have been marked for being swapped out, and normally those pages would then be swapped out to disk. This is a very slow device. You'll have 5 to 7 millisecond seek time and the rotational latency, so there's a lot of delays in that. VMware is basically saying, let's have a small area of our DRAM where we're going to keep compressed pages that compress at least 2 to 1, so the memory management is easier. And so this is an approach that is being used today in a very popular product, VMware's ESX 4.1. I found this article just 2 nights ago. Justin Ratner is the CTO of Intel, and he talked about a variable precision floating point unit. Variable precision floating point? Why would you do that? We have IEEE 754, which is a perfectly good standard for 32-bit and 64-bit floats, and that is being used with every chip that offers floating point processing, including the ones from ARM, where we're carrying those around in our pockets in our application processors. What their chip does is it figures out what level of precision is necessary and only takes the data in that format and crunches it at that level of bitness. That's very interesting. So he also made a key point. And think about what I said earlier about how I was introduced to compression, how personally I was introduced. In audio, the question is the audio quality good enough? And that is a key question. What Mr. Ratner said was, there is no diminished resolution on images, at least not that the eye can see. And then that reminded me of Samplify's tagline, simply the bits that matter. If we preserve the bits that matter, will our answers change? And that's a longer discussion, but I just wanted to plant the seed, and I thought this was interesting. So here's the leading CPU company in the world saying that it's okay to do 8-bit or 6, 12, and 6-bit and 12-bit precision once in a while, and they will discover for you. That's the other thing about this algorithm. They will decide when it's okay to back off on the precision. So here's a little more details. This was presented at ISSCC just in February, and this is the same article that the previous slide mentions. And here's the reason that they're doing this. Today's floating point math wastes energy, time, and storage by using worst-case precision everywhere. Well, there's an interesting question. How does Intel know that that's worst-case precision? Here, let's do a theoretical exercise. Let's say you have your favorite algorithm and you've been using single precision floating point numbers, which are 32 bits long, 1 sign bit, 8 exponent bits, and 23 mantissa bits. If you run your same algorithm using all zeros in the smallest bit, in the 23rd bit of that 23-bit mantissa, instead of the zeros and ones that it came with, would you get the same answer? Just about everybody I've talked to doesn't know. They don't know what precision is required to keep getting the right answers. And this is people from Lawrence Livermore Labs, people that are doing scientific computations all over the world, supercomputing designers. It's a hard question. So this 24-bit, 12-bit, 6-bit, this is a good idea, and this is kind of where Samplify is going. Here is a circuit from Intel, which is just on a test chip, but the direction they're going is, well, maybe we don't need the precision in calculations all the time. Samplify is asking a slightly different question. If you don't need the full precision in calculations all the time, do you need the full precision when you're taking the chip, the operands on and off the chip? So we're solving the I/O problem. Intel is trying to address the compute problem. So on to APACs. So this is now Samplify stuff. What we compress is numbers. So now I'm on the third part of the talk's title. We have multi-core, the memory wall, and numerical compression. Many of you may not have heard that phrase before, but what's a number? It's either an integer or a floating point number. It might have lots of different bit widths. You might have 8-bit, 16-bit, 32-bit ints, maybe even 64-bit ints. For floats, you almost always have 32-bit floats or 64-bit floats. So that's a number. And what APACs compresses is numbers. Ints, floats, and frames come in, typically from the faster memory, and then they go through a redundancy remover and a bit packer. Let me talk about those phrases. Compression is basically the art of making things smaller in a way that people don't notice. If it's lossless, a redundancy remover says, oh, I've seen this kind of stuff before. If you're doing Lumpel-Ziv and you're doing Alice in Wonderland, you're trying to compress the book Alice in Wonderland, the word Alice occurs a lot. So if you put the word Alice in a dictionary, and then whenever it occurs, 5 ASCII characters, A-L-I-C-E, you just send a, let's say, a 2-byte pointer there, you'll get some compression. You're sending 2 bytes where you used to have 5 bytes. The redundancy remover is doing that with numbers. Many of you may be familiar with PCM, pulse code modulated signals, and DPCM, differential pulse code modulation. So you have a stream of numbers, 1, 10, 20, and then you subtract them. 10 minus 1 is 9, 20 minus 10 is 10. And sometimes, if you just take the difference of the stream of numbers, then you can compress that. So the redundancy remover, basically, just think of that as a fancy differentiator. Now, the bit packer, this is where the kind of goofy variable bit width stuff happens. Huffman coding, Golomb-Rice coding, where basically you're trying to say, I've got 14 bits here and 17 bits there and 6 bits here, and I want to mush them all together in a way that I can losslessly take them apart again. So that's what bit packing is about. So a redundancy remover followed by a bit packer. Packet header generator, the way Samplify Apex works is it takes n samples in a row, compresses them, slaps on a header, and then sends that out, and that's a packet. N can be anywhere as small as 64 samples and as large as you want to make it. You know, a practical limit might be 1,000 or 2,000 samples. So that's how it works. Question?
Frames on the left is video frames?
It could be, yes. This particular word is applying to HD or video, uncompressed video frames. And let me point out that a frame of images, RGB per pixel, let's say the most common video format is 8 bits for red, 8 bits for green, 8 bits for blue. So 24-bit pixels for 1080p, kind of a mainstream HD video application. You have 1,080 rows and 1,920 pixels per row, and that's how you represent it. What are those? Numbers. Images are numbers. Image processing is just DSP. I should point this out. It was mentioned in my introduction. Every customer, I think without exception, has said, oh, I can only ever use your lossless mode. True story, we've been working with GE Healthcare in Waukesha, Wisconsin. They make CT scanners, computed tomography scanners. We've been working with them since January 2007. Their chief engineer, Bob Senzig, good friend of mine, he told us in the first meeting, Al, if you ever say lossy, we're going to have to show you the door. GE will never use lossy compression, full stop. So, in 2 years, Mr. Tyler.
Yes, a quick question on the samples. You said that you align the samples and you slap a header on.
Yep.
Is there a notion of the sample rate? Because obviously, the samples are meaningless without the timestamp in which the sample is taken. And what's the delta in time between adjacent samples?
Think of it as that every compressed packet carries the same number of samples. So if your packet size is 64, every compressed packet represents 64 ints or 64 floats. So the notion of time actually flows with the samples. The decompressor knows I've received 2 packets, 64 samples each, so I must have seen 128 samples. So the notion of a sample in a computer or a CPU, the time element typically goes away. We can talk about it a little more afterwards, but Samplify began life compressing A to D converter samples. So we very much have the sense of real time. So, back to the GE story. After 2 years and, I don't know, a few gigabytes of CT data, 16-bit integers, we got on average 1.9 to 1 lossless compression. Sometimes it was as bad as 1.7 to 1. Sometimes it was as good as 2.7 to 1. So in a fit of silliness, Bob Senzig said, well, what if you just did 2 to 1 all the time? We'll never use it, but let's just see what that does to our images. So what we were compressing specifically for CT scanners was the X-ray data that was being digitized. They need somewhere between 3 gigabit and 40 gigabits per second of data that goes across the spinning donut of a slip ring. For those of you that haven't had a CT scan, you have a table that goes through a spinning donut. On one side of the donut is an X-ray source that shoots X-rays through your body in a very thin slice. And then it has basically a rotating sensor that goes around the patient and captures the attenuated X-rays. That combination generates somewhere between 3 gigabits per second and 40 gigabits per second. So we compress that data. You need a less expensive slip ring, which you have to send that 40 gigabits across, and then the data gets captured in a RAID array in real time, because the image reconstruction software, which takes the raw data and turns it into the pretty pictures that the radiologists look at, that process is non-real time. So a 30-second scan might take 10 minutes to put together. So there are tens of thousands of dollars in BOM cost if you could do even 2-to-1 compression of CT sensor data. Now, having said all that, a CT scanner is just a fancy camera. And the arbiters of the quality are radiologists. So in 2009 and 2010, we wrote a paper with GE Healthcare and with Stanford Hospital, and we had to look at 400 image pairs side by side, and we asked the radiologist a simple question. Is the image on the left or the image on the right, was it created with 3-to-1 compressed X-ray data prior to image reconstruction? But it gets compressed and then decompressed, and then it goes into the same image reconstruction algorithm that GE's always used. And the conclusion of the paper was, well, he couldn't tell the difference. He could tell the difference on 4% of the image pairs, 17 out of 419. And on those 17, where he correctly guessed, oh, the right one must have been created by compression, the key question is, would his clinical diagnosis have changed? And the answer was no. So there's an example. Yes, sir?
Just out of curiosity, how much space do you need to save on actually without
They don't have a capacity problem. They have a bandwidth problem.
I know, but I'm just curious about how bigger.
We typically get requests for putting together at least a terabyte of storage, but the more important number is, let's say you needed to do 40 gigabits per second. That's 5 gigabytes per second sustained going into a disk drive or going into solid-state disks.
So, and how long does a CT scan be?
A CT scan can be somewhere between, the max length is somewhere between 30 seconds and 1 minute. Yes, sir?
Yeah, were you going to cover the fixed rate compression because it seems to be unitless, so I was clear on that.
Okay, so you specify compression ratio in increments of 0.05. So 2-to-1, 2.05-to-1. Compression ratio is unitless. And fixed quality, if there's any communication engineers in the room, this is typically specified in dB. If you have 16-bit A to D converter, the 6 dB per bit rule says that that's 96 dB of dynamic range. So with Samplify, you could say I need 87 dB or 86.5 or 86 dB of dynamic range. Yes, sir?
Your 3-to-1 CT compression was intra-slice?
It uses a combination of looking along the rows, the slices, between the rows, and then between the views, but not very far. Just one view back. Any other questions? Okay, this is an important one. Lossless, fixed rate, fixed quality. I got on this topic by talking about GE, who said they would never use lossy. Well, they haven't paid us money for it yet, but we are well along the way. They have to get what's called 510K approval from the FDA before they could use something like this. And anyway, that's enough of that. So here's something else that's really important about this. So imagine you had a compressor that could help the memory bottleneck. Yes, sir.
Sorry, just before we leave that, 510K approval assumes that there's another product out there that you can directly compare it to. The FDA has clamped down on that due to some issues they've had with being too loosey-goosey with 510K. So what would they, do you have any idea what they would compare that to?
It's not a very well-known fact, but the CT industry has been using compression for about 20 years now. And rather than calling it compression, what you need to do with the FDA, and this is from a woman who used to approve CT scanners at the FDA who we've talked to, she said you needed to call it an efficient encoding technology rather than a compression technology. So wordsmithing is alive and well at the FDA. But not to be too glib about that, to be specific, most A to D converters in the front end of CT scanners, first you have a scintillator, which turns the impinging X-ray into light, and you have a photodiode which turns light into current, and then the current goes into an A to D converter that turns it into a 20-bit or 22-bit number. Because of the characteristics of X-rays, which when the signal rises, the noise rises, which is kind of a weird thing, and when the signal goes down, the noise goes down, they've realized that they can encode this by using 2 exponent bits and 14 manticipits. And that format is affectionately known as funky floating point. You don't have a sign bit, but you've got 2 exponent bits and 14 manticipits. And that is, it turns out, almost perfect theoretically to match that square root relationship between signal power and noise power. So, okay, let's talk about size and speed. Apex is software and Apex is hardware. We will be, the last couple slides are where Samplify is going in the next 6 months, where we'll have some software very soon and some hardware not that farther after that. Here's where we're aiming for in terms of latency, 30 clocks, and where a clock is a CPU clock. So if you have a 2 gigahertz CPU, you're talking about 500 picoseconds as a clock. Basically, we have some gates that need to get filled up. We fill up a pipeline, and then after that, out pop the compressed packets. If you think about DDR memory interfaces, where the latency of RAS and CAS, row and column strobes, might be 30 to 40 clocks, we're saying that you could hide the latency of compression hardware associated with a memory controller or a DDR controller within the RAS-CAS setup of DDR. So the latency is an important parameter here. And here, 100K gates. For those of you that aren't that familiar with silicon, this just say tiny. If you know what a bond pad is, this fits under a bond pad. Is it easier to make DDR3 run 2 to 3 times faster? Or is it easier to maybe try this compression thing, and if you're bold, maybe even in a lossy mode, as opposed to a lossless mode?
I'm assuming your 30 clock latency doesn't apply to images.
It applies to everything. Images are numbers. So imagine you have 1920 pixels coming in. It's RGB or YUV, doesn't matter. So after you have seen 3 times 15, 45 pixels, you'll start getting out the compressed version of the first triplet of color that you put in. So when you get a little bit ways into the first raster, you start getting data out. This is really different than H.264, where you say, okay, I'm going to put in 2 or 3 frames, and then I hope that I'm going to start getting some stuff out. That's a lot of latency. That's milliseconds of latency.
Then you were talking previously in the GE case about doing 3-dimensional prediction. In fairness, you were talking about doing 3-dimensional prediction.
Let's say that I've saved the first row of CT samples. A good number is 1,000. There's typically 1,000 sensors in this direction across the patient. By the time I get to the first sample of the second row, I've already seen the first sample of the first row, and I can do that subtraction. So by definition, that latency is 1 sample, even though I'm 1,000 samples behind when the first one came in. Relative to when the first sample of the second row comes in, I do a subtraction, and it's a latency of 1. Another question?
So, what kind of compression do you use? I mean, what do you call your compression method?
We call it pixie dust. No. It's a time domain algorithm that I dreamed up in my garage in 1996 when I fell in love with the problem of doing lossless audio compression. So all the techniques are time domain, and I've got a few patents out there. You could just type my name into uspto.gov and read all about it.
And of course, both ends you have to have your algorithm run.
An excellent question. If we were still in the A to D converter business, if Samplify were still in the A to D converter business, we would have to convince the A to D manufacturers to put our compression in there, so they'd need fewer pins or lower speed SerDes, and then they'd need the decompressor in whatever device they're feeding it, if it's a CPU or an FPGA. Think about the problem that we're trying to solve. Here we have multi-core processors. We're trying to solve a memory bottleneck. And what do you do with memory? Well, you write to it and then you read from it. And the processor by itself has no inherent bits when it starts up. It's always given the bits from somewhere else. Imagine this scenario. You're a multi-core CPU, And whenever you write data to your memory, you compress it. Whenever you read that data back, you decompress it. So it's basically at both ends. If the problem we're solving is a DDR memory bottleneck, you have to write to it before there's anything to read. That's when you compress. And then when you read it back, you say, oh, I know that this was in the compressed area. Doesn't mean that's the only kind of memory you have, but you can set it up that way. Exactly. There was a company called SandForce that was purchased by LSI Logic a while back. SandForce followed Intel's lead, put Lempel ZIV lossless compression into their DDR memory controller, or their solid-state disk memory controller, and they just said, well, if it gets better compression, we're ahead. If it gets 1.2 to 1, okay. If it gets 1.6, even better. What they said is use our controller, and you'll get longer flash life. That's a good sales pitch. Okay, so let's talk about, now, one of the questions that Samplify often gets is, well, yeah, but how many numbers are there in the world? I'm going to ask a different question tonight. Have we seen any chip manufacturers put special silicon on that does math? Thank you, sir. Okay, Intel has this thing called MMX, goes back to the late 1990s, I think, and then SSE and AVX, Advanced Vector Extensions. And instead of, if one add per clock is good, then if you could do 4 adds in one clock, that must be better. You need some special registers to do that. You put your 4 operands in, and then you need to add them to 4 other operands, and off you go. Our friends at Xilinx and Hans's current employer, Altera, when they started putting DSP blocks onto FPGAs, they made the DSP guys like me so happy. Because all of a sudden, instead of having our algorithms run at like 1 megahertz for DSP on a TI 55X processor, now we're running these things at 50, 100, 200 megahertz because of these DSP blocks. And these don't take a lot of the area, maybe 5 to 10%, but somebody decided it was a good idea to put math, arithmetic operations that are supported by silicon onto the chip. AMD's Bulldozer, same thing. They have their own version of SSE. IBM's Power 7, they have something called Altivec. Our friends over in the UK, one of the very few successful chip startups in the UK, ARM has something called Neon, and it's the same thing. Neon hasn't been all that successful, but they have something to sell. And so let me summarize. If CPUs and GPUs have floating point units, I'm going to go back to the 8387 FPU, they have SIMD, single instruction, multiple data, SSE and AVX as being examples. Then wireless baseband, wherever you have wireless baseband, what is that? DSP, what are the operands? Typically from A to D converters, they're ints. And ARM Neon is a SIMD instruction. H.264, frame buffers, what do they have in them? 8-bit, 10-bit, 12-bit ints. And the FPGA DSP blocks. These are dedicated arithmetic blocks that somebody before me, way before me, decided, some marketing guy said, boy, we better put that arithmetic acceleration processing on there. And I bet Tylera may have multiply blocks on its fabric. And if you went to the trouble of putting all that math capability onto your chip and it's taken up 5 or 10% of your chip, why wouldn't you want that math to run faster if it could? And you could get the same results. All right, here's another slide I only found 2 days ago. Has anybody heard of Embassy? Spec Int, Spec FP? So Embassy is a industry consortium. It's a benchmark company. I joined up, and I wasn't quite sure why, on a new working group called FP Bench, Floating Point Bench. And what they're trying to do is for embedded processors, they're trying to allow people to do apples-to-apples comparisons in the $2 to $4 range for chips that do floating point processing. And what I discovered about a month ago was quite interesting. What the group decided with guidance from people from Intel and Microchip and ARM and Qualcomm and NVIDIA is that if you run an algorithm, you have some C code, you compile it, and you run that algorithm with a floating point accelerator on one chip, and you compare it to the results on another chip, if 15 out of, I don't have this number on here, if 15 out of 23 manticipits match, that's good enough for FP Bench. And when I heard that, I thought, what? How can that be? That can't be right. Well, then I found this little nugget here, which I want to go back to this thing. See this little subtitle here? Why doesn't my application always give the same answer? If I'm a DSP guy, I'd be really worried if, if I had something like that. But it turns out that there are quite good reasons why, or at least explanations. There are good explanations why you don't always get the same answer. And this made me nervous here. There's inherent uncertainty in the result of most calculations involving floating point numbers. Isn't this the reason that we invented IEEE 754 in the first place, so there wouldn't be this inherent uncertainty? Well, it turns out, if you go read this paper and about 30 other articles like it that I went through, that compilers do weird things, and if you put your operands in a different order, you're going to get a different answer. There are optimizations that most people like to turn on because they make the results come out faster. Let's say, like Mr. Ratner alluded to, we'll discover when 12 bits is good enough for you. Just trust us. But this trade-offs thing is good. So what is Samplify offering? We're offering you not all the bits you started with in I.O. in exchange for getting your answers perhaps 3 times faster. Back to Schlumberger. This is not... Let me go in a different direction. There are companies in supercomputing where the biggest waste of time is where the supercomputer guys have kicked off a simulation and they got to wait a week and a half to get their answers. And while they're doing that, they're reading articles and they're going home and working on the lawn or something like that. And then they come back after 10, 12 days and they go look at their answers. They spend a day visualizing their gigabyte result, and they fly around in it with all this supercomputer visualization stuff. And then they say, oh, I need to tweak 2 parameters. And then they go home, and then they can plant the roses because they got another 10 days they got to wait till they get their next answer. If they could get an answer that is about in the right direction in 5 days, do you think that they want to take advantage of that? I think they would. So this is all about trade-offs. When we told our pro audio customers in 1994 that they could use Dolby AC2 at 4:1 compression and play more disk drive channels off, the first thing they said was, oh, the audio is crap. It must sound terrible. When they convinced themselves that, oh, actually they were getting the same results, the audio sounded the same, and that's all they cared about, and the people they were selling the CDs to didn't notice any difference, they'd rather have 20 audio channels coming off there. So what we're selling in terms of capabilities or results is that if you get your answers faster, you're probably going to be happy. And the answers put you in the right direction. It's like one of those gradient descent algorithms. As long as you're going in the general direction, you're doing the right thing. Okay, where's Mr. Cache? Somebody asked the question about cache. Okay, here's the slide I was alluding to. All right, now here is a paper I found last night. Dark silicon. Has anybody heard that phrase before? Dark silicon. Okay, you guys are ahead of me. So here it is, percentage of dark silicon, transistor underutilization. So imagine you built a chip and nobody used all your transistors. That would be disappointing. I would be sad. Okay, here's the problem. 20 megabytes. I don't have that die shot, but I think it's like 45% of the chip area for this 8-core Sandy Bridge is cache. And that cache, my friends, may go dark in 10 years. That's what the point of this paper was. And this is like a refereed IEEE journal. This is not some guy making stuff up. So at 22 nanometer in 2012, 21% of the chip will be dark, and at 8 nanometer, over 50% of the chip will not be utilized. That's scary. So the point of this slide is that as much as we're working to scale this memory wall, the memory wall has now jumped over DDR. The memory wall is now in the cache, and people are starting to say, smart people, that we're not going to be able to use all those transistors. So if you can have higher information density, if the numbers that are in your L3 cache, let's say, were compressed, there's an interesting idea, and then you decompress it when you're going to L2, think about what kind of delays there are between L2 and L3 cache. Could we do that kind of a jump? Uh-oh. Yes, sir?
So, I mean, that's fine, as long as you have a single processor. What happens in a NUMA environment where you have multiple sockets? You can actually, this socket's processor can access the memory in the other
Yeah. I think a lot of that has to do with how likely is it that they're going to have the two separate sockets have data that needs to be identical.
That probably happens pretty often. Really.
Yeah, I don't know what the statistics are.
I also don't know the statistics, but the compilers would do things like that.
Yeah. So cache coherency in general is a difficult problem even when you're on the same chip. If you have to go off the chip, this is where QPI and hypertransport currently off chip, you know, Intel and AMD have thought about that. Okay, this is my last example about where a numerical compressor on chip, off chip would be useful. One of the ways that you get 20-to-1 and 30-to-1 compression out of H.264 and MPEG-2 is you do what's called motion estimation. You have a frame of pixels here, and then you have the frame of pixels that came just before it. And you say, well, I got the eye of a little man right here, and where was that man in the previous frame? Let me go find that eye, and instead of sending all those 16 by 16 pixels, 256 pixels at once, I'm going to just send a pointer to where those 16 by 16 pixels are more or less in the previous frame. That's how they get compression. But think about what you have to do to figure out where did those 256 pixels go? Well, you have to do a search. You have to do a brute force search. That process is called motion estimation. In the decoder, it's called motion compensation. What it requires from all processors is they need to have one or more frames stored off chip because they can't fit the frames on chip. So this is where the memory wall comes in. Here's the video processor on chip running H.264 or MPEG, and here's the DDR memory off chip that's storing the reference frames. And we are not new in this. There's actually prior art going back. Anybody do patents there? One of my favorite things to do. There are patents going back to 1998 about putting lightweight compression in the interface so you store lightly compressed frames in DDR memory. Now, at some point, the complexity of the algorithm starts to matter. And if the algorithm could be used for something else, that would be useful. So imagine you had a DDR controller that could compress ints, floats, and the ints that are frames of video. Yes? Yes, that same general technique that you described, sir, is typically not done for one pixel at a time. It's typically done for what's called a macro block. So it would be just a little too difficult to try to correlate one pixel all over the place. So they typically tend to do it in macro blocks. Thank you. All right, this is to give you an idea that we've been around the block a few times. So here are some of the lossless and lossy compression results that Samplify has generated. Wireless baseband and RF signals, computed tomography, ultrasound both before and after the beamformer, images and video, oscilloscope signals. Prior to CT, that was my highest throughput real-time signal oscilloscopes. They can run at 40 gigasamples per second. Radar and sonar, high-speed imaging, and graphics textures. So all of these are integers. And notice that we have two columns. The lossless compression ratio, 1.5 or 2-to-1. 80% of our customers, they send us their data. They've never tried compressing it. We can get them somewhere between 1.5 and 2-to-1 lossless in most cases. Where it gets interesting for me is they say, you know, it's great that you have lossless, but those varying compressed packets, they drive me batty because I need to have rate matching buffers at both ends of the link, and that costs money. It would be better if I could just say, well, just give me 2-to-1. Just give me 2.3-to-1. And can I have a register where I can just type that number in? Well, with Samplify, you get that. So here, the ratio is up to 6-to-1, lossy compression, where the user has decided their results have not changed. And we actually use measurements. For instance, if anybody's worked in the wireless area, 3G wireless is now merging to 4G wireless, and they use quantitative metrics like error vector magnitude, peak code domain error, adjacent channel leakage ratio. So basically, you hook up your signal to an Agilent scope or an Agilent signal analyzer, and it just tells you what the numbers are. So imagine you've got a fiber optic cable going up and down your cell phone tower, and you compress the data down here and you decompress it up there by a factor of 3 to 1. That means that your existing 3 gigabit per second fiber with compression of 3 to 1 can now carry 10 gigabit per second of data. And we've done this test, and it passes. It passes the EVM and PCIe specs.
So is anybody using that in production?
I cannot say today. Let's just say that there are a lot of base stations being deployed with 4G capability. And on the floating point side, we're relatively new here. We're only about a year and a half into this, maybe 2 years. But these applications here, hydrodynamics, car crash simulations, CFD, computational fluid dynamics, can get in the range of 1.5 up to 4 to 1 compression while their answers stay the same. Did their answers stay the same is a longer conversation with the customer. But when we show them this stuff and I tell them that I have 400 gigabytes of customer data at Samplify, they start trusting us that we have done this before many times.
How does your image compression compare with the HP local stuff?
HP, yeah, local 1 and 2. It's comparable in compression ratio, but they tend not to do as well with lossy. They were built to do, just barely under lossless. And their complexity is also larger in terms of gate count. So one other thing that's somewhat unique about us, we were asked by one of the graphics companies to compare ourselves to texture compression, which is common in many graphics applications, DXT3 and DXT7, 7 being the most modern. This graph right here, the bluish graph, I think it's blue, I'm colorblind. That's Samplify Apex, and we're comparing ourselves to DXT7, and we're using this metric called structural similarity. Has anybody heard of structural similarity? Okay, there's a new one. It's a metric that says if I have a reference image, my original one, and a processed image that somehow is different, when human beings look at the processed image, how similar do they think it is compared to the original image? And structural similarity is a way you can quantify that. So we've used this to good effect going back to the CT paper we wrote with the radiologists with GE and Stanford. And so the point of this is that here are textures that the texture compression algorithms are getting worse performance than Apex does. And all they can do is 8-bit color, and all they can do is decompress. They can't do real-time encoding like Samplify can. And we can also do different formats and color space decimation, et cetera, which DXT3 doesn't support. Here are high dynamic range images. So this is newer cameras, or instead of just having 8 bits or 10 bits per color plane, now they're starting to have 16 bits per color plane. Maybe not 16 linear bits, but better than 8 bits. And again, compared to block code 6, which is in the latest Microsoft DirectX image processing, we're getting, at the same compression ratio, 6 to 1, we're getting better quality than EC6 does. Okay, I'm going to wrap this up here probably in the next 10 minutes. Here is what most Samplify customers do. And hopefully this will remind you of something that maybe you guys have done. You have a real world something you want to measure it, temperature, pressure, cloud cover. You have a transducer that monitors that, turns it into either a voltage or a current, and then you run the voltage or current through an A to D converter, and out come numbers, integers, 8 bits to 20 bits. Often, let's say more than half the time, before this number actually gets to a storage device, it's gone through some little piece of C code and got converted to a 32-bit float, and that's where the problem begins. Because what happens is the people who acquired the data forget to tell the people that are using the data that we're not actually giving you 32 useful bits. They just think, oh, well, you just ended up with 32 bits on the disk. That must be gospel truth of what the number is. So, and then what do? Well, they process 32 bits and 64 bits, and They say, well, that's all. Those are my choices, 32 bits or 64 bits. What Samplify is proposing is a way to scale the memory wall where whenever you leave the chip, you compress the data. And you might be going to DDR, you might be going to disk. When it comes back again, well, you just decompress it right before it gets to cache. Don't tell the cores. They're still going to get 32 and 64-bit floats. They're still going to get their 32-bit integers. By the time it gets to the core, it's the same size it always was. It's just we took a few of the bits away and we solved the memory wall. Well, we didn't solve it, but we're scaling it. We're making it be smaller with a knob that the user controls in increments of 0.05. So a real-world example. People like to, at least if you're a DSP guy like me, you don't feel like you've gotten your money's worth unless you actually see a waveform. So we're about to see waveforms. So we have a pressure transducer that measures pressure from 0 to 30,000 pounds per square inch. And the accuracy, the analog accuracy of this transducer is plus minus 3 psi. The data goes to an A to D converter that has 20-bit resolution. And what the people who sent us this data insist on is that they have a resolution of 0.001 psi, even though the gauge has an accuracy of plus minus 3. WTF. Okay, but we're gonna help those people see this as an error. Okay, so here's a happy waveform. Here's 1 million samples. Thanks to MATLAB for drawing me a nice picture. The y-axis, 0. That's like being out in space, no pressure. And then 1600 psi. So you have this periodic waveform. You can just imagine what causes that kind of a pressure waveform. If I zoom in on the 1500 sample somewhere in the middle here, this is what that waveform looks like. You get a bouncy bounce waveform. If you take an FFT of the signal, you'll get this spectrum over here. Now, this spectrum, if you don't remember anything else tonight, pay attention to this spectrum. The spectrum has a peak at 79 dB. And literally, you just take these numbers from 0 to 1600, 64-bit floats with 0.001 resolution, and you dump them into an FFT in MATLAB, and out pops this spectrum. The noise floor is at 28.7 dB. Well, this is called the eyeball SNR, signal-to-noise ratio. You got a peak over here, and you got a floor over there, and you have a dynamic range of 51 dB. 51 dB is an interesting number, which in one slide I'll tell you why it's interesting. So if you were going to evaluate the quality of Samplify's APAX lossy mode, how would you do it? Well, the easiest way to start is, well, what's the error look like? So you take the original signal, and you subtract it from the signal after it goes through a compressed-decompressed pass, and we don't care if this is ints or floats or images or whatever it is, and then you get an error signal. We do one more really important thing, and the next slide hopefully will convince you that lossy compression has more than a snowball's chance in hell of working. You do a Fourier transform or a power spectral density transformation of the error signal, and that gives you an error spectrum. Now, the error spectrum is very important because it tells you from DC to Nyquist, are you messing up the original signal? Okay, so here's our bouncy bounce waveform, 1,500 samples worth. And plotted here is a blue waveform and a red waveform. Can anybody see the blue waveform? Hopefully not. That gets plotted first, and then the decompressed waveform gets plotted on top of it. And if you have a good match, then you should not be able to see the blue waveform. Of course, I want to subtract the signals from each other to get this error signal. So here we have the range from 281 to 1,071. That's the peak over there, or maybe that's 281. Yeah, that's 281 and 1,071. And then the error is plus minus 0.16. Is that good? Is that bad? Well, I don't know. If the accuracy was plus minus 3, I'd say an error of plus 0.18 is not that bad. At 3-to-1 compression, we have an error of plus minus 1 psi. It's still within the standard deviation of the plus minus 3 of the analog sensor. Now, here's hopefully the convincing slide. These are the error spectra at 2-to-1, 3-to-1, and 4-to-1. So 4-to-1, you'd expect it to have a worse error, so it should be closer. Here's the original spectrum from 79 to 29, dynamic range of 51. 51 dB. If we use the 6 dB per bit rule, 9 bits times 6 dB per bit is 54 dB. So we say, well, we've got about 9 integer bits. The range of the original signal was 0 to 30,000 psi, and the accuracy was 3. So that's about a factor of 1,000. 1,000, 10 bits. So that holds together. Here's the important part. We are somewhere between 19 and 23 dB below the noise floor of the original signal. The error introduced by compression is between 19 and 23 dB below the noise floor of the original signal. Okay, this is where Samplify is going. We want to give you a knob that sits in your silicon. My friend Arup is here from Intel, and we hope that somebody like Intel or NVIDIA or Qualcomm or Tylera or MIPS would put our stuff in there as an IP block to give you a flexible knob with very tiny area. Look at that area number, 0.06 millimeters. That's pretty small. And we want to be around the bond pad. We want to be around the DDR controller. And what do we get for it? Well, the user gets to dial in. We have a couple other things I won't talk about tonight about an automatic methodology where the user doesn't even need to know. They need to trust us. They need to be aware that, you know, there might be some magic going on here. But the people we're selling the benefit to is the scientist who's out there replanting roses because he's got to wait 10 days till his answers are done. So that's who we're selling this benefit to. We're not selling the fact that we got a knob here. We're selling the fact that we know how to set the knob, and they're going to get a really important benefit that will change their life. So what are we doing? We're trading gates for pins. I don't know too many other algorithms that do that. You give us that much area, and you don't need to have 3 DDR memory controllers on here. You can get away with 1. The phi rate stays the same. Notice that the DDR has no idea we're sending compressed bits to it. It's still running 240 pins at 1.6 gigahertz for 1666 DDR3. The effective throughput increases. What the CPU sees, what the core sees, is now 2 to 3 times more data. And gates for pins is controlled in software. I didn't do that. Maybe that's my signal I'm running out of time. All right, I'll hurry now. So Samplify has raised $22 million in 2 investment rounds. Charles River Ventures and Formative Ventures are our venture capital partners. Schlumberger and Mamiya are our strategic partners. This is what we're doing with Apex in software. Notice the speeds. 60 to 400 megasamples per second per x86 core. And these are the products that we'll soon be offering for sale in software. A library where you get a compress and decompress function. You get a profiler function, so if you're new to compression, you just say, well, here are 3 files that are representative of what I'd like to compress, and please tell me how much compression I could get. Remember that little SNR slide? That's the kind of stuff we're doing there. And a mem copy, that's a very common C function. Just take this blob of memory and put it over there, and while you're at it, compress it. MPI, message passing interface, is used in supercomputing, so we'll be coming out with a line of MPI send and receive accelerators. File system operations. This is the slowest, you know, the turtle in the race is the disk drive. So if you can compress and decompress things that are running at 60 to 80 megabytes a second disk drive interfaces and have those run 3 to 4 times faster, it helps your capacity and it helps your bandwidth. And then for several users, they'd like to have a CUDA DMA function that allows them to use compression in the GPU environment. And then here's the one I'm most excited about. If you got some kind of an ARM processor and you're going to have a DMA controller on an ARM AXI4 bus, that'd be a cool little IP block to integrate in. So that all of these things, the DDR controller, the PCI controller, and the USB interface, they can all use this little block. Just on the way out to DDR or on the way out to the PCIe bus or QPI bus, compress and decompress. We'll be prototyping this on the Xilinx Zinc. Anybody heard of Zinc? ZYNQ?
Never heard of it.
Yes. And soon, Altera will have a Zinc-like object called SoC FPGA, which I'm sure will be much better than Zinc, but it's just not available as early as Xilinx is. Okay, and also important is that the IP, this little hardware widget, and the APAC software I showed on the previous slide, they have the same application programming interface. So how does DMA work? You give it a source address, a destination address, and then number of samples to move. Well, we just do it in terms of packets. How many packets do you want to move instead of how many bytes do you want to move? And you get this mode, bypass, lossless, fixed rate, fixed quality, 2 bits, and a parameter. How much do you want to compress? Or how many dB do you need for fixed quality mode? All right, almost done. So multi-core CPUs and GPUs are here to stay. I/O is a problem, and it's not going to get any better. We're out of pins. SerDes is hard. The dark silicon problem, I only heard about that 2 days ago, and I'm starting to get worried. So we need to do something differently than we have in the past. There's FPUs, SIMD, and DSP processing is dedicating silicon area for math. What we're suggesting is that we add an I/O accelerator that allows you to get the same results you always did, but just to do it faster by reducing the memory wall. The area is small. If you're going to put APACs in silicon, it's low latency. Customers control the knob. This is very important. If they want to use lossless, let them use lossless. If they want to wait, instead of 10 days, they'll get 7 days and it's lossless. That scientist may be perfectly happy with that. He may be happier if he only had to wait 4 days, but the customer gets to make that decision. 2x to 6x, this is important. Sometimes we get 8x, but not very often. But 2x falling off a log, 6x, with a little work, we can usually get there. And then the numerical killer app is motion compensation, motion estimation. This is a problem that I tend to stay away from all the image processing stuff because there are 10,000 smart researchers trying to get an extra 1/10 of a dB of performance out of H.264, and I don't want to compete with them. But I think with APACs, we're not trying to compete with them. We're trying to solve a different problem. We're trying to make their motion estimation and motion compensation use less memory. Yes, sir?
So another question out of curiosity. So when you actually use your multi-core DNA as a natural drive, so have you actually thought about where, for encrypted drives, where you put the encryption before or after you have?
In general, encryption and compression are orthogonal, although we get asked this question all the time. There's nothing inherently safe about just compressing your data and hoping that nobody knows how to decompress it. Encryption should be a step that's done after compression.
Yeah, that's what I thought, because if you do it before that, you might lose some bits.
Yes, that would be a bad thing. Yes, sir?
This may be related to your last clear point. There was at some point wavelength lossless compression. Is this something that is similar to what you're doing? Is it unrelated?
It's mostly unrelated. Wavelets are for it's usually consumer type media, not for generic instant floats. And in summary, we have a website, samplify.com. I have a bunch of business cards up here. If anything that I said interests you and you'd like to talk to Samplify further, please take a card. And for those of you who are RTL savvy and are looking for new opportunities, please come talk to us. Thank you.
Thank you. This is for your hat collection. This one you don't have yet. I would like to thank you, and you didn't compress your presentation, obviously. We were a little over time. And it was also not just good enough. It was actually an excellent presentation. So thank you very much.
Great. All right. Thank you, Hans.
There you go. For your one more.